Okay, welcome everyone to this seminar this morning. I'm Bill Gould, the director of the USDA Caribbean Climate Hub. And we have a few folks here in person and other participants virtual in this seminar. We're going to discuss a project monitoring resilience, observing the Earth at night here in Puerto Rico and U.S. Virgin Islands. I'd like to thank you all for attending. This is a collaborative project with Leidos Incorporated and the USDA Caribbean Climate Hub. I'd like to thank the Office of the Chief Economist for some support for this project, as well as the Hub team and the Leidos team for this collaboration. It's been ongoing for a year, and we'd like to share some of the progress on that report. We think we've developed a really important new data set for looking at energy vulnerabilities in the region. And we're looking forward to sharing those with you. I'm going to pass the microphone to Lorelei Bracero, who's been she's the GIS lead for the USDA Climate Hub, and she's been liaison with the Leidos team. So Lorelei.
Thank you, Bill. Morning, nice to meet you all. My name is Lorelei Bracero. During the research seminar, we'll present the preliminary results of the nightlight patterns after power outages in Puerto Rico and U.S. Virgin Islands. And this study seeks to assess the vulnerability due to the lack of electrical power of different sectors, such as agriculture and forestry. NASA Beers and Black Marble products were analyzed to create interactive tools to visualize nightlight conditions in an area of interest. This collaboration is between the Hub, Dr. Nora Alvarez, Dr. Bill Gould, and myself with Leidos. Now I'll present Dr. Peter Boucher and Hector Tarrido from Leidos. Dr. Peter Boucher is an award-winning geospatial scientist who has designed studies and developed methods to monitor everything from power outages to piles of endangered rhino scat. He's passionate about connecting people to nature through outreach, new tech, and Earth observation data. Hector Tarrido Picart is a world-class products designer, developer, and researcher who can design software and buildings with equal fineness. Hector draws from his extensive experience in app design, architecture, and GIS data systems to develop products with global impacts. He's passionate about fostering resiliency and improving energy access in his native Puerto Rico. So welcome, Dr. Peter and Hector.
Thank you.
The floor is yours.
Thank you so much.
Thank you, Bill and Lorelei, and thank you everyone for attending and listening in. We're really excited to present to you today some of our efforts to make some new data products from nighttime lights data that will help with monitoring resiliency and vulnerability in the wake of natural hazards. And so I'm here with my colleague Hector, as he was introduced to. I'm a scientist at Leidos, and Hector is a product designer, as Lorelei said. So first, I'll tell you just a little bit about our team. So we're from the Office of the Chief Scientist in the health and civil sector at Leidos. And we're really a high-performance team. We're small but mighty of scientists, technology specialists, and solution architects. And we work with government agencies providing scientific leadership, technical supports, primarily for geospatial and remote sensing Earth observation data. So in addition to working with USDA in this case, we also have other customers such as NASA and other government agencies that you can see listed here. And for this contract and for others, we focus on developing data and tools that's more actionable for tracking things like natural hazard impacts and resiliency to them. And today I'm going to tell you a little bit about one that we've developed here with nighttime lights. So what are nighttime lights? Here's an image to get us started. And this is actually showing you, this is a combination of satellite images from the last 10 years or so. And it's summing all of the lights seen from that satellite at night. And so what you're really seeing here are areas of dense human settlement, right? You can see where the cities pop out. San Juan lights up. And it's really showing you patterns of human behavior. And so this is the data we're working with. And this is just a single image, but what we have are 10 years of nightly observations. So 10 years of data went into this. So it's quite a lot of data to work with, but you can already see how that might be useful. So more on what an NTL data actually is, or nighttime lights NTL is what I'll refer to it as. It's also called black marble for the reason that you can see right here in this gorgeous image from NASA. So it's a data product that's distributed by NASA and collected on NOAA satellites. And they collect nightly observations of the Earth all over the globe at around 1:30 a.m. And they've done that since January 2012, and it's still ongoing. And so what it's capturing is the brightness of light being emitted by human settlements. So street lights, house lights, anything you can think of that you might put in a light bulb, right? And because of that, it's related to human activity. And studies have even shown it's related to socioeconomics. Things like GDP match up to how much light you emit. Land use change, you can imagine if you have, say, a piece of forestry equipment going in the middle of the forest in the middle of the night, you would pick that up in a pixel, in a very bright light and a very dark pixel. So you can track land use change in that sense. And in this case, what we're really focused on is looking at the impacts of and the recovery from climate hazards. And we're doing that by tracking power outages and blackouts, apagones, as you say. So a little more about how nighttime lights data is collected. Again, NASA builds the instruments and NOAA operates the satellites. And this is the suite of satellites you can see right here that has the VIIRS instrument on it, which contains the day-night band, which is the sensor that actually takes pictures of the Earth. And the two satellites right here that have the day-night band on it are the NOAA 20 and SNPP, as you can see. So they're in the bottom right there. So it's a collaborative effort between NASA and NOAA. And they release these data products to the world. It's publicly accessible. And these data, again, have been used for all different kinds of applications. And I just wanted to show this image briefly to illustrate a few of them. Things like human health events, pandemics. You can track illegal fishing. Light pollution is a big one. And power outages and electrification globally. And really what this is, it's sort of an objective measure of whether the lights are on, right? Across the globe. So it's the same kind of picture being taken everywhere, every night. So it's really our closest thing to an objective truth of whether the lights are on, right? And we want to use this, in this case, to track something like climate resiliency. So we're looking at the capacity of community and organization to respond to and recover from disasters. And, you know, as many of you know and have experienced, these impacts are increasingly severe in the Caribbean. And so we can actually use these data to start to track resiliency and response to these. So both the impact, but also the response of people. How are they changing over time? Are they switching to more renewable energy, or they have more generators that can switch on in the wake of a natural disaster and therefore turn the lights back on? And can we use that as a measure of how resilient a community or an organization is? And so what we've done for USDA is we've taken the night lights data set from NASA and we created a new nighttime lights data set that's more actionable and user-friendly. So we've taken the NASA data and we've also built on top of it to try to create some new metrics that are going to be really useful for hazard impacts, identifying vulnerable communities, and measuring resiliency. So I'll give you a quick overview of what the data looks like before we get it. So this is if you were publicly accessing the data from NASA. So they lay out the data on a huge grid like this across the whole globe. And then they split it into different tiles. And so you download data for a tile, and each tile has a file for every single night. We'll look into that further. But if you want to look at somewhere like Puerto Rico and the US Virgin Islands, you want to grab this tile right here, H11B7. That's just its row and column in this big grid. Then once you grab that, say you need to grab there's one file basically for every night the satellite is observed. So each one of these boxes represents a whole tile that you would download and a whole file covering the entire area, and you would download one of those for every date. Now, again, I said that there are there's an observation and a file for every single night since January 2012. So this is a lot of data and it's a lot of tiles to download if you're just going from NASA. And each tile is a ton of data in it, right? It's 2,400 rows by 2,400 columns. Each of those pixels within the image is about 500 by 500 meters, more or less, which makes each tile being roughly about 1.2 million kilometers across. So it's a lot of data. And then if you think about, maybe you just want to look at one pixel or a set of pixels for a city like San Juan, right? Then you need to pull out the pixels from there. And each of those pixels has its own 10-year time series, right? There's a whole stack of data, both in time and in space, in this case. And so what we've done is that instead of having to download all of these files from NASA in order to get that 10-year time series, is that we've taken the data and we stacked it so that you can see all of the pixels through time at once. So it's a much more actionable data set, right? So you have this, so every time you try to get a pixel, you have the data from the last 10 or 12 years or so, right? And originally, if you went to NASA, you'd have to get about 4,400 files to do that, right? Now you just have one that has everything for the last 10 years. Right at your fingertips. So you can see this stack of pixels might be turned into something like a time series right here on the right. So this graph, don't worry about all the fancy figures on it, but it's just it's showing you time on the x-axis and radiance, which is the brightness, on the y-axis. Don't worry, we'll look at some other graphs and I'll explain them a little deeper. This is just to know we have one of these for every single pixel within the time. So it's a ton of data, and we have this historical record that we can then use to start to look at trends, look at impacts, and look at dips in the time series that might be indicative of things like power outages. And so what we've done is we've taken that big record, that record of nighttime lights data, and we've generated a new data product on top of it. And we're calling that data product an anomaly score. And what these are, they are normalized scores of your deviation from your business as usual or brightness as usual, if I'm going to call it. So it's the deviation from what you would expect the brightness to be for a given time period. So if it's brighter than normal, it's going to be a positive number. If it's darker than normal, it's going to be a negative number. And if it's just the mean value, the normal as you expect it for looking at a pixel, then you would label it 0. We'll look at it in a little more detail. And just for some background, the way that we produce these anomaly scores is we actually adapted this open source NASA algorithm. It's called the COLD algorithm. It's been developed for the last 2 decades from many different research labs, and we've taken that and built on top of it. So I'll say this once, and then I'll probably say it again at the end of the presentation, because I think this is the most important thing to learn, is that you do not need to be an expert on nighttime lights data to use an anomaly score. The whole point of producing this data set is that we're making something that's actionable, that's user-friendly, and that you can grab and run and try to contextualize with other factors like, events, dates of big events, or maybe the power grid and the length of roads and things like that, that you could use to actually contextualize the events that happen in the power outages that you might have recorded via directly from a power company. And so right here, when we make an anomaly score, just briefly what we're doing is we're trying to measure the magnitude and the direction of the difference from what is the normal brightness or the brightness as usual. And we're correcting for a bunch of stuff, including angular effects. The instrument, for instance, as you can see illustrated on the right, is actually seeing cities and settlements from different angles as it goes over. So every night at 1:30, it's taking a picture, but it might be doing that from a different angle. And as you can see on the right, that might change what the brightness is, when in fact, and what we want to know is, whether brightness went up or down due to something like a power outage. In this case, you might have an effective angle causing the brightness to go up or down, right? But we actually want to remove that, so we did it. We took it out, and your anomaly score is corrected for that. We also corrected them to be comparable across space, so you compare the anomaly score of one pixel to another pixel and across time. So you can compare the anomaly score in January 2012 to the anomaly score in January 2024. So I'll just show you a little bit of what these anomaly scores look like in time, and then we'll jump back over and maybe look at them in space, because I think it'll then maybe stick what these are actually, what these actually look like and what they're useful for. So right here, I'm showing you a graph again with the date on the x-axis, so going from January 2012 to December 2023 on the bottom. And then the y-axis is showing you the anomaly score. So where I've written brighter and darker, and then in the middle right there is the normal brightness, as you would think. So 0 means this pixel is as bright as it normally is. But what you can actually start to see here, oh, I've also colored it. So green means brighter than usual. Purple means darker than usual. And if you have a quick look at this, you might notice it's pretty even spread around 0. But there is one event right here in 2017 that really pops out, which is when Hurricane Maria happened. And you can see the anomaly scores dip quite low, showing that for this pixel, this is a pixel from San Juan, there were a series of anomaly scores for a couple of weeks afterwards that were really quite low, much lower than all of the other time series. And that could be indicative of a blackout for an extended period of time. So you can already start to see maybe how this data might be useful looking at it in time. Oh, and I should say too that every single dot on here, so that's derived from a nightly observation. So every dot is an observation for one day. So you're looking at over 4,000 points, 4,000 days of data right here. So yeah, so when you look at that period during Hurricane Maria, you're actually seeing multiple days of outages. Great. So now let's take a step back and maybe look at it in space as well as time. So right here, first I'm going to show you the nighttime light's radiance, which is the brightness you would see directly from the sensor. So this is the NASA data product that comes out. And right here, this is looking at San Juan, the greater area around it. And you can see on the left, I've taken the mean nighttime light for every single pixel in this area. So the mean irradiance, the mean brightness before Maria, and then on the right, the mean brightness afterwards. You can see a big change right here, right, which might be indicative of power outages in the area because the lights aren't on as we pass over for an extended period of time. But when you're actually trying to get the spatial distribution of that, it could be difficult. But when you look at the anomaly scores, that spatial distribution pops out right away. So again, this is the same time period on the left and the right. On the left is before Maria, on the right is after Maria for San Juan. And it's 6 weeks of data combined into a mean for every single pixel. So on the left, you see maybe a more scattered version. There's some areas that are appearing brighter than usual, some areas appearing darker than usual, but there's not necessarily a clear pattern that we can see. On the right, you can clearly make out some very extreme darker than usual values, and they're clustered together, maybe representing neighborhoods and areas that are all losing power at the same time. And for an extended period of time, right? This is 6 weeks of data combined into a single value. So this is the mean. So that means that those areas are especially vulnerable at these periods of time. So let's look at some more graphs, maybe zooming out to the whole island. And this is following the same color scheme, right? So purple is darker than usual, green is brighter than usual. And this is the 6 weeks before Maria, for the entire island. And then the 6 weeks after Maria. And already you can start to see areas across the entire island that are more vulnerable, that were more maybe potentially less resilient or more impacted by these areas. And we can really use this to identify vulnerable areas that had more impacts, areas that might need more help, and also maybe try to understand how we can do better in the future in terms of supporting them. But really, we're providing this data set to enable scientists and staff at USDA and elsewhere in order to take these data and put them in context, right, and make them more actionable. These data they're amazing and they show us incredible spatial patterns, but As for what it means or why different areas are being brighter than normal or darker than normal, that's all has to do with context, right? Has to do with policy and has to do with people and how they are responding to natural disasters. But I would still say that what we've created here is some of the best data that we can use to actually link nighttime lights to power outages and to measure something like resiliency. You could use it to get something like the magnitude of change before and after. Because that anomaly score is normalized and is comparable across space and time, right? You can really compare different events in time, so events that happened all the way back in 2012 and events that happened 2023 and beyond, as long as the satellite is still collecting data. You can identify areas of vulnerability, and you can also try to figure out how long it takes for areas to get back to business as usual. And you can do that on a per pixel basis, so that 500 by 500 meter square pixel. There are some limitations that I'll just briefly mention here. One is that when there are clouds, the satellite cannot see through clouds and record a data point. So if it's cloudy for an extended period of time, then unfortunately we can't get any data. So that's always a limitation of satellite remote sensing, at least passive remote sensing. And even in this, you might wonder, oh, why are there so many white spots sort of in the middle of the islands? That's because those areas are likely cloudy for an extended period of time. I think they're mountainous areas. And the other thing I'll say is that context is everything, right? This is an incredible data set. It can do so much. But what we really need are people to come in and provide context for what we're seeing. There's so many different factors, human factors, environmental factors, social factors, that influence how we respond to natural disasters and events and how we get the power right back online, right? So it's not always a one-to-one relationship. And I would just put that out there. So anybody who's interested in using this for their research, it will take a lot of context in order to understand. So you don't have to be an expert in nighttime lights. You don't have to be an expert in the algorithm we use to create an anomaly score. You do need to be an expert in the context for the events for the time period that you're studying. And I'll just finish up my section with a few more images from Fiona before and after, or actually this is just after Fiona. So this is the 2 weeks following Fiona 2022. And this is the mean anomaly score for the period. So again, purple is showing you darker than usual pixels, and green is showing you brighter than usual pixels. And you can see the spatial pattern is pretty different than Maria, which may be something that some of you have a lot of context for, having lived through it or seen maps of it in advance. And just looking very briefly at something like the path of the hurricane as it passed through, I can already see that the area of the island, maybe down near Cabo Rojo, that seems to be largely affected in the bottom right, or sorry, the bottom left. You see a lot of dark purple pixels. Seems to be similar to where the path of the hurricane went through. And I also know there was a lot of flooding along the south due to this hurricane as well, which you can clearly see here. So I hope that this data set enables you to contextualize some of these events. So we're going to be delivering over a decade of nightly observations for you and nightly anomaly scores. And now it's up to you guys to provide the context and understand and try to use it for resiliency metrics. So thank you so much. With that, I'm going to hand it off to my colleague, Hector, who's going to tell you a little bit about the data products that we have for providing that context. Thank you.
Thank you. All right, so I'm going to talk about some of the enriched data that we have built to be able to actually interpret this information at different spatial scales. And I'm going to be talking about it from the visualization point of view, just to make it easier so that it's lighter on the science and more heavy on what the imagination can provide in terms of the research questions that you can answer. In addition to the nighttime line star file that Peter was talking about, we're also providing aggregated information as a vector file at 3 different spatial scales
The first one being at the 1-to-1, the Earth pixel polygon. The second one at the level of the county or the municipio, and the third one at the level of the barrio or the subdivision. We're also developing a dashboard that's going to help understand how the Earth pixel is seen across time and across space, and that provides poses a series of challenges given how the data is the pixel actually behaves in terms of the model that is behind it, and also the breakpoints that Peter was showing. So there's specific challenges of being able to actually aggregate the sector data on a temporal spatial scale so that it matches what we're seeing at the Earth pixel. The Earth pixel, the more or less the timestamp for the observation is around 1:30 in the morning. But of course, not all information that researchers might want to answer the question actually is mapped to that high resolution time series. But what we have done is we have gathered the information that we could get from the census and from other sources and tried to get as accurate timestamp as possible. In this case, for the census, we have gathered for each year for the barrio in Puerto Rico, the African American Community Survey Act, and then for the U.S. Virgin Islands and for Puerto Rico, the census, the decennial census. In this case, because the data is from 2012 to 2024, we grabbed the decennial census from 2020, which is the one that falls time range that we're making observations. There's some caveat to this information that comes from the census, which is that the census had a different type of participation due to COVID, and specifically in the U.S. Virgin Islands that affected the numbers. So just got to be careful with what the interpretation that you gather out of that. And then the at least in the U.S. Virgin Islands, the American Community Survey does not happen because of just the spatial resolution of it. It poses privacy questions. So, and then the final thing is that for Puerto Rico, we have additional data sources that are not available for the U.S. Virgin Islands, specifically the energy infrastructure, which helps to get a better insight into what's happening at each individual pixel. And then also some additional information as for researchers, we don't have the landslide USES information for the U.S. Virgin Islands. And so what we're providing to the community is a composite of all this information so that it actually snaps more or less into time with the Earth pixel, so that you can, when you aggregate across time, you can do it at least at the level of here. So if you wanted to understand and visualize it as a graphic, then you have the challenge of visualizing the nighttime lights as a map with time, right? Running across as like a movie rather than looking down. We also have the challenge of the different spatial resolutions and how do we aggregate the different spatial resolutions, given that the pixels the smallest set, but then how do you aggregate up to the county and the barrios, and then the observations made from nighttime light, matching that with the temporal nature of the census being every year or 10 years. Here, there's also another consideration to take for the Earth pixel, which is that they don't necessarily fall very nicely into what the land is and what is water. And I was using this to help users understand that the pixel size might pick up light in places that are in an edge condition, like water or an island. And so in the energy grid information, it shows that there's nothing there, but it might actually be activated, because even just a small sample of a building or a boat, that could actually trigger the nighttime light, the radiance to actually be activated. And so these are all conditions in Puerto Rico specifically that match that. And so just again, as Peter was saying, we're providing you with the information, but there's all this spatial context that you also need to consider when actually processing the information. In this case, the marine is a good example. There's no distribution directly mapped, but we know that they light up because of all the cluster of boats they turn their lights on. There's also other considerations when aggregating spatially. In this case, I'm using the example of Mona and the Seychelles. They do show up in the nighttime light. The radiance is there, and the anomaly score also shows up. But also because it's not inhabited and there's no energy infrastructure, you gotta make sure that you consider that, taking into account population count, just simply the infrastructure count. So just be careful with how this information is aggregated up, and Ponce shows up also in different municipalities where there is, if they're part of the municipio, but the islands are clearly not inhabited. But some of them might have infrastructure in them, like Caja de Muertos or Mona, but just something to take into account when doing the spatial aggregations. These are some of the diagrams that at Leidos we do to kind of understand at a very basic level what is it that we're looking at. And this is just the whole design process of how we think about time with a map as a linear scale that can then actually be used to filter the information and explore. And so for us, it's a constant iterative process and a constant discovery process where, we think we might have a solution, and then when we start actually playing with the data, new problems pop up, like the models, each individual pixel not adding up at the spatial scale, or the anomaly scores just not actually being visualized in the way that we expected when we start aggregating. So it's not an easy problem to solve, just because of the nature of we're gathering information across time, we're stacking it vertically, at a horizontal level. If you were to think about it as a map, then it has the breadth of geography. And this is an early version of what the tool that we're developing looks like. It's automatically based. See enter. This is the mouse. Yes, it's not a video. Oh, there we go. Okay, so on the left you have the vertex pixel isolated only for what's on land. On the right you have the anomaly score and the rating score at the bottom. And the idea is that to be able to explore the data, you don't need to have a GIS environment. Quickly filter for the barrios, for the municipios, for the different islands in the Pittsburgh Islands. And the anomaly score or the time range is going to update automatically, and then you can click on the graph, and that graph then update the map. And we're building this tool for internal research so that then you can then jump into your GIS environment and conduct much more complicated spatial analysis. But again, because this data is so rich, we thought that this would be helpful just to be able to grasp it and not get lost in the details of how to open it in a GIS environment, how to aggregate it. Just this tool will give you this kind of first entry point into the data set. The way that we have chosen to aggregate this and compare it to the different spatial scales is by treating the vertex pixel row and column as a unique ID. Then from that, you can abstract that to be either the center of the pixel or the actual reprojected square of the pixel sphere. For the counties and the sub-barrios, what we did is we we provided a list of unique IDs of the beers that can be matched via an attribute join. And then for the beer pixel itself, the GIS environment that has a unique ID that match to the counties and sub-counties and some of the subdivisions, so that you could also filter for the barrios or for the municipio. Within the Verse pixel, the way that we aggregated was anything that was coarser than the Verse pixel. We just did mean aggregation. So the Verse pixel, and that's enriched, has the USDA canopy, the ecoregions, health and emergency infrastructure, transportation, FCC communication infrastructure for mobile cell towers and hand radios on towers. The energy infrastructure for Puerto Rico, which that includes substations, transformers, transmission lines, distribution lines, and switches. Basically, the whole infrastructure is there accounted for. And the topography, the mean height, mean slope, and then for Puerto Rico, the USDS landscape sustainability as a mean category aggregated for the pixel. And this a good way of kind of seeing how this aggregation can help you understand recent events, such as the transformer story that happened about a month ago. It can help you really understand the impact of how the transformers are distributed spatially across the island, how that relates to the distribution lines, and why in Santa Isabela they needed a transformer, and why it was picked up from Caguas rather than any other municipality, and why they couldn't just ship the transformer down the highway. They had to actually ship it over the sea because of the nature of the topography and the nature of the roads themselves not collaborating to that. And also the tree canopy, the coverage of the tree, and having such heavy equipment that's so big, going through not only the distribution lines that tend to be low, but also the trees, which you have to trim and cut. For the subdivision, we have information that's for each barrio. In Puerto Rico, we have the population and elderly statistics, health insurance coverage, the median household income and poverty rates. And then from the USDA, we have aggregated on this for Puerto Rico, total farms, livestock, poultry, dairy, hydroponics, and eggs, and more coming soon. And so for Puerto Rico, this is, again, going back to this point that I made about time, we have it from 2012 to 2022. And for the US Virgin Islands, we have it from only for 2020. And we don't have the USDA information for the US Virgin Islands. So that means that you can match the various information to make studies around the population, total households, elderly, and other types of demographic data that you might want to compare the impact of the outages and high anomaly scores compared to the census information. For the county, at the county level, what we have done is we've taken the economic census and the US Census and joined it both to Puerto Rico and the US Virgin Islands. In Puerto Rico, we have the total sector, a number of establishments, annual pay, and number of employees. And for each of these, then we have each niche, bakeries, anything related to food production and food consumption, grocery stores, supermarkets, healthcare facilities, restaurants. And then for the US Virgin Islands, we only have a high-level total sector information. So again, you can measure the economic impact of power outages with aggregated all the way to the county, and then be able to do some studies on that as a researcher. So, you know, in the case of the transformer, you could look at the number of businesses impacted and how relative to the distribution of businesses across the island, how that the fact that the anomaly score might have gone up because of the failure of the transformer from Hurricane Maria, that would have adversely affected the businesses and the economic development of that municipality. So these are data sets that we're gonna give you all so you can actually explore in your GIS environment. They're packaged as a geo package, so you can open both on ArcGIS and Quantum GIS. And we look forward to seeing what the type of research that you do combined with the time series Spears Pixel. And we just can't wait to see what the results are. And we're here to help. We're here to make you successful in understanding that data, and hopefully we get to see some exciting research in the next couple of months. Thank you very much.
Thank you very much, Peter and Hector, for this great presentation. And now we have some time for questions. First, here in the audience, is there any question for Peter and Hector? Okay, online, you can raise your hand and we can unmute your microphone for any question that you might have.
Of course, yeah.
Or you can type it in the chat box.
Laura, I've got a question, maybe while we're waiting.
Yeah, okay. Deal.
I guess for both of you, thinking about the anomaly scores, are there like for each, I guess, pixel or area, extended area, are there like a set of metrics in addition to just the anomaly score or the mean score? You guys thought about those metrics and what they might be so that we can compare those metrics with other things, that context that you guys described?
Yeah, absolutely. Yeah, thank you so much, Bill, for that question. We have thought quite a lot about other metrics that you could derive from this data. The original bill was to say, okay, nightly anomaly observations, right? So we're going to start with the highest resolution temporally data that we can get. So that's why we did nightly anomaly score observations. But once you have those, you can really start to think about other metrics. Like I think I mentioned things like the time to recovery. I think that could be a really important one for every pixel, right? So after an event, how long does it take to get back to a normal brightness, right? Or even just the magnitude of change. How far down did they dip for one hurricane versus another for a given area, and what does that mean for a pixel? So we definitely have a lot of ideas about what to do with it, and I think maybe through a collaboration between different use cases and through us and on the technical side talking about the data products, we could probably come up with even more. So yeah, do you have anything to add to that?
I mean, I think that one of the assumptions is that the nighttime night is observing the energy structure. And so I think, and in the case of Puerto Rico, for each pixel, we know what's in each pixel in terms of distribution lines, transmission lines, the substations, and I think that that's one of the correlations that could be made is the amount of radiance in relation to what's under what we know is there in terms of energy infrastructure. And that compared to areas where it's more remote, and we know that like the urban areas have been high concentration of it's specifically distribution lines, and in the remote areas of the island and other parts of the world, it's not as much present, right? So I think that there's a metric there that we explore, because you could perhaps do something about how the energy infrastructure is actually operating based on like the ground truth of what's laid out. But again, it's highly contextual, as Peter has mentioned. You gotta be very careful how you go about it, right? But I think that's something.
Is there any question from the audience? Okay, yes. So Sarah Hall is asking where and when might these data products tools be available?
I think that might be a question for you guys.
Yeah.
Thank you for your questions. Yeah, we're planning to use our Forest Service data archive in the future to publish all this data. We already begin, the Leidos already begin doing all the metadata. So we have to figure out the best way, but for now it's data archive. And we'll keep you posted when these data sets are published. But for now, we're just using internally and figuring out, as Hector mentioned, the best outputs and the best products. But yeah, feel free to contact us if you're interested in other data sets for now. Thank you, Sarah.
Maybe I'll make a comment to that. This is brand new. I mean, this is the first time this has been presented outside of our team. And so we're excited about that. And I think it's also a new way of using this global data.
Yes.
So,
Yeah.
That's exciting too. And we do have the intention to have a methodology paper that will be a citation for those scientists that want to use this data. So you have a reference for how the data was prepared. But we're also at the Climate Hub, we have some intentions of looking at vulnerabilities in local agriculture and forestry sectors. But definitely we're excited to see what kind of collaborations and ideas other scientists have in using this. So we think this is like the first stone of a whole new way of looking at energy vulnerabilities in Puerto Rico. But also, hey, this is a global data set. And there's likely intention that these kind of data will continue to be collected by NASA, and something that we can think about the future of how to use this information.
So now we have a question by Luis Rodriguez Cruz. He's also part of the Caribbean Climate Hub. You haven't met him, but he says, first of all, great presentation and work. And then he asks, can these data be turned into variables to be used in linear models or others such as structural equation models, where these anomaly scores can be included with other socio-ecological variables to understand vulnerability related outcomes? I'm thinking of what you mentioned about contextualizing the data.
Yeah, I can answer that. I would say yes, absolutely. This is what we hope to happen, right? Is that we created a data set that is validated and the methodology is explained. There's still a long way to go with the validation, of course. It is brand new. But I think through these kinds of studies, we can start to see the real potential of it. And yes, absolutely. This is for modeling. This is for visualization. We've done everything we can to make an actionable, user-friendly product that you can take and run with. So yes, please try that. I'd love to see what happens.
Okay, I see Diana is typing a question or a comment.
Oh, great.
Well, Diana's typing. My original question about metrics, I was thinking in terms of like LiDAR data. It's like return data. An individual data point doesn't mean that much, but when there's a ton of metrics that you derive from LiDAR data, and I think there's some potential with the anomaly data to look over time at, for example, what's the variability in anomalies?
Mhm.
What are the trends in anomalies, like Peter mentioned? What are the extremes in anomalies? What's the are certain areas have more sort of breakpoints where there's extreme events versus other parts of the landscape. And those are the kinds of things to respond to Luis that you could get as a number or a pixel or an area. And then those could go into statistical models where you compare them with other data. So I think we're kind of just at the beginnings of thinking which metrics would be most important. How could we extract those from the pixels or from the barrios, municipalities, or compare them with island-wide metrics, or compare urban versus rural metrics. I think there's a lot of possibilities.
And I'll add that if anybody from the audience have ideas of any other sector or any, as Luis mentioned, feel free to contact us or throw it in the chat because it will be great to see other applications of the data sets. So
Diana, thank you for the great presentation, very exciting work, and she can't wait to see it available, data available.
Thanks. Thank you. It's great to hear.
We have a little time. I'll keep.
Sure, yeah.
We have a couple of products out of this, and one are the data sets, and the second is the visualization tool. And just to share, at the moment, we kind of visualize that tool as something not necessarily on a website for the general public. It's a little complicated to understand that, the data and figure out the context. But we will, for the moment, consider it a tool of the Climate Hub, something that for sure our team will get up to speed so that we can share that with individual groups or researchers or agencies that may have interest in this. And we'll have to kind of play with the visualization tool a bit to really see where its value is. And then I think it'll be our intention to try to share it and communicate it so that other partners, other parts of society can realize that value from the tool as well.
Diana mentioned that I was thinking this is great data sets for behavioral data, for example, bad nightly behavior or other biodiversity. Do you have ideas on how to answer a question like that?
The bad, like this.
Bad, murciélagos.
Oh, okay, BAT. Yeah, I mean, I think that you can always, any type, we have the ecoregions that we join to the pixel. Any type of ecological mapping that the researcher might have, they can always join it to that specific pixel level. And then they can take the slides of the anomaly of the time series from the nighttime light that they want to study, and then they should be able to pose some questions and get some answers. So, for example, if they know where the predominant bat ecosystem is, I'm going to go here and say, sans like Isabela, Hoyer, where the Cuevas de Camuy are, right? Like just filter for that, and then understand like the population of observed there, and then the researcher could take the before an event or after, and like say before Maria or before Fiona and after Fiona, if they have that information of bat population, and they could compare that to the anomaly score ID, so whether it's brighter than usual or darker than usual. That way they can start getting to answer the question what an event had both on the nighttime lights of the area and the population, right? So they could join that. It requires a little bit of spatial savviness, but it's perfectly doable.
So we have time for one more question or comment. You can unmute yourself if you would like to share a comment at this point. Okay, well, thank you very much. I'll be to go there. I could say goodbye.
well, thank you everybody for attending. Thank you for the awesome colleagues that I have from the Hub for all the help. Thank you for the presentation. And I'll leave with the final remarks. We have 4 minutes. Thank you for the ASL interpreters. There's
one question.
oh
Oh,
We'll take it.
yeah, go ahead.
Okay, can you share the contact info in the chat?
Oh, yes.
Yes, sure.
Definitely.
And great presentation.
If you want our
Yeah,
email,
Sarah.
if you go 2 or 3 slides over, you can see them.
At the beginning.
It's at the very
the
end, actually, if you just go over 2.
There you go.
There you go.
And we'll send that over to chat.
Okay, sure. Well, I'd just like to say thank you to Peter and Hector and Boucher and Nora for the presentations. And I encourage folks to get in touch with us if you're interested. Stay tuned for further developments. We're going to continue working with Leidos over the next year, exploring the data and products. So wish everyone a good day and thank you all for joining us.
Thank you.